Okay, so we're working on applications for solving log and exponential equations. So Natalie's saving up money for a down payment on a new car, right? Now, she currently has $5,000, but knows that she can get a loan with a lower interest rate. Why is that good? Because she pay less money, right? If she can put down $6,000. So the more money she's got, the less likely she might default on the loan. So maybe the better rate she gets, right? So if she can invest her $5,000 she has right now today in some money market account that earns 3.6% annually compounded monthly, how long will it take Natalie to get up to $6,000? So she wants to throw her money into account so that it can grow $1,000. Okay? And then once she gets that 1,000, then she's going to put her money towards a new car. So what do we need here for compounded monthly? Well, that's going to be AT equals P 1 plus R over N to the NT. So we need to know what P is. Okay, P is the original, that's the principal amount. How much does she have right now? She's got $5,000. Okay, 5,000. All right, what's the next number I see? $6,000. That's how much she wants to have in the future to put it down. This is the future value. So A of T, all right, is $6,000. All right, if she invests her 5,000 now in a money market account at earning, now this is my interest rate. So the rate is 0.036. Okay, convert to decimal, move it over twice, right? Okay, compounded monthly. Monthly means n is equal to 12. It compounds 12 times per year. All right, now the time. The time is what we're looking for. How long will it take? How long will it take, Natalie? That's what we're trying to figure out. We don't know how long, but we're going to figure it out. So plug in our players. So 6,000 equals 5,000 times 1 plus 0.036 over 12 times 12t, raised to the 12t, rather. So what do I need to do first to solve this problem? First thing you do is divide by 5,000. Divide through by 5,000. What do you get? You get 6 over 5 equals what? 1 plus 0.036 over 12. Okay? Raised to the 12t. Now, this right here, I can simplify. Okay? This in here, if I type this in my calculator, 1 plus 0.36 divided by 12, 1 plus 0.036 divided by 12. This is 1.003. So I have 6 over 5 equals 1.003 raised to the 12t. I'm trying to get t by itself. T is up here in the exponent, so I need to get rid of this base here, okay? So what I'm going to do is I'm going to log both sides. So I'm going to log both sides. What do I have in here? 6 over 5. Okay. And then this is equal to what? It's equal to the log of all that stuff. 1.003 to the 12t. What happens to my 12t here? It comes out front. 12t multiplied by ln 1.003 equals ln 6 over 5. Okay, I'm trying to get t by itself. So what do I need to divide by? Divide by 12 ln 1.003. Divide both sides by 12 ln 1.003. So t is exactly equal to the natural log of 6 over 5 divided by 12 ln 1.003. So type that in your calculator, that big old mess there. All right, if you type that into your calculator, ln 6 divided by 5 close parentheses. Oh my goodness, let me start over. ln, 6 divided by 5. Let's go outside here. Divide, and then what do I have? I want to do parentheses 12 times ln of 1.003. I'm going to close my parentheses. Okay. I think I got one too many parentheses, but I think it's going to work. So 5.072. 5.072. So 5.072. Now, would you walk up to somebody and say, yeah, it's going to take you 5.072 years, right? So my time is in years, right? The time is how long will it take? It will take that many years, okay? So 5.072 years. Or, maybe like 5 years and 1 month, maybe. Somewhere around there, 26 days. How did I get 26 days? Well, this 0.072, how many days are in a year? There's 365, right? So 0.072 times 365, that gets me like 26 days. So that's, 26 days is, like a month. So 5 years in a month, you'll get your money. That's basically what they're saying there. Okay? All right, let's shrink this up. And put it up here, and then let's talk about half-life. Okay? So here's an example. A of t equals a0 e to the negative 0.000121 t. Right? The a of t here is the amount of carbon-14 at time t. And this a0 is the initial amount of carbon-14 at t equal to 0, at time equal to 0. What you want to do is you want to find the half-life of carbon-14. Okay, so this is the number of years required for half of carbon-14 to decay. So you've got the equation. Now we're going to figure out what the half-life is. Okay, so how do we do this? Right? When you are working on a half-life, okay, literally half of it is going to disappear. So all you got to do is say 1/2 equals whatever my base is, okay? So e to the negative 0.000121 t. Now, why does it work this way? Because look, the initial amount is a0, but after some amount of time, my a of t becomes half of what I started with, right? So when I divide through, right, when I divide through by a0 on both sides, I cancel and all I'm left with is 1/2. Okay, we talked about that in another video, but this is just a shortcut here. If I have a half-life problem, I do 1/2 equal to whatever this base is and ignore the initial amount going on here. Okay, so how do I solve this for t? Natural log both sides. If I natural log this, what happens to e and the ln? Well, they cancel each other, so I have ln of 1/2 equals negative 0.000121 t. If I divide both sides by this constant here, I'm going to get my answer. Okay, so t is roughly, when you type that in your calculator, you're going to get, what are you going to get? About 5,728, okay? Which just so happens to be matching the half-life that I told you that carbon-14 had. All right, cool. So I want to find the number of years necessary for some substance that has 2.3 grams of carbon-14 to go to decay down to 1.5. So how do I do that? I start with my formula. A of t equals what? A0 e to the negative 0.000121 t, right? And so I'm told that I started here and I want to go down to here. So my starting value is A naught, that's 2.3. And my ending value where I want it to stop is 1.5. So how do I solve for t? Divide both sides by 2.3. Okay, so now I've got 1.5 divided by 2.3 equals e to the negative 0.000121 t. So what do I do from here? I log both sides, ln both sides, and it gets rid of my e. And so I have ln 1.5 over 2.3 equals negative 0.000121 t. Divide by 0.000121. And what do I get? I get my solution. When I type this in my calculator, ooh, that's an ugly approximate equal. That's 3,533 years. So after 3,533 years, okay, I get down to 1.5 grams, right? So that's less than a full half-life, right? Because look, we're not going down, we're not cutting it in half, but we are decreasing it some, okay? So I've got one more problem, and it has to deal with population. So assuming that there are currently 600 billion people on the planet, which there's more than that, but let's assume there's 600 billion, make it a nice round number. And then our growth rate is 1.9% per year in population. So the population grows 1.9% every year. How long will it take Earth's population to reach 20 billion? 20 billion is a pretty big number, okay? So when we're talking about population, let's use our population formula. P of t equals PO, P naught, A to the t, okay? Now, the PT, this is the population at time t. The PO, this is the initial, the starting population. Okay. The A, this is my base, which is the rate. All right, it's either rate of growth or rate of decay. And then the T is obviously the time in years. For this particular problem, we've got it pitted in years. Okay, so what do we know? What are the numbers we know? 6 billion, that's how many people we started with on the planet. Where rate of growth is 1.9%, so my R is 0.019. Okay, my PO is 6 billion. 9 zeros. What else do I have? Want to see how long is T, so that's what I'm looking for. How long is T? Okay, so until we get to 20 billion, so P of T equals 20 billion. All right, so let's plug in our values into our formula. So 20 billion equals 6 billion times A. Okay, how do I get my base A? Well, I know my rate is 1.9% added on to, what do I start at? I start at 100%, right? If I'm staying the same from year to year, I stay at 100% year to year, okay? But if I'm growing, then that 100% may turn into 105%, right? And then the next year, 105% more, and so on. If I'm decaying, maybe that next year I'm getting down to 95%, whatever. If my decimal here is 1.9% growth, that means that the next year will be 101.9%. That's what that means to have a growth rate here. So how do I convert this? I do 1 plus whatever my rate is, right? The rate happens to be 0.019, okay? I add here because the population's growing. If this word had been decay, then I would subtract the 0.019, okay? And so then that would give me a different answer. So 1 minus that would give me like a 0.9. Ooh, I shouldn't have done this. 81, right? So that would give me a 0.981 rate instead of this 1.019 rate. Raised to what? The t. That's what we're looking for. Okay, so I want to solve. So how do I solve? I got to divide here. So let's divide here. So duplicate again, divide both sides by 6 billion. Those cancel. All these zeros, cancel all these zeros. Field day going on, right? So I have 20 over 6 equals 1.019 raised to the t. Now 20 over 6 simplifies. That's like 10 over 3. How do I get rid of my base here? I'm going to log both sides. Okay, if I log both sides, what happens to the t? It comes out front. Okay, so I have ln 10 over 3. And so how do I get this by itself? I divide both sides by ln 1.019. And so when I type that in my calculator, I'm going to get like 63.967. So what is this telling me? We have a 1.9% population growth rate for the next 64 years. Then we're going to have 20 billion people on the planet, which is kind of crazy to think about. Okay, but that's how populations grow unless you get, overpopulation, and then, bad things can happen. Famine can happen, diseases can happen. Mother Nature has a way of taking care of itself. When you get too high density of people living together, unfortunately, that's just how it works out. All right, guys. Well, this ends the application for Chapter 7. We've only got one more video left. All right, good luck.